Hello, we are continuing our work with Chapter 3 in Section 3.2, and in this particular video we'll focus on the properties and how to apply the properties to finding derivatives. Alright, in our section here in 3.2 we have a handful of properties that work with that work with taking derivatives, and a lot of that it should be something that's similar or something that you've already seen with the regular derivatives. Yeah. So here it says for the first one, the derivative of a constant times a vector valued function is the constant times the derivative of vector valued function. That's the scalar multiple idea. We've seen a similar property in regular derivatives. The sum and difference, the derivative of the sum and difference is equal to the sum and difference of the derivatives of the functions. Now this is similar to a scalar multiple, except the function, the scalar is actually going to be a function. So I want to focus on the f of t that's in this formula, and notice that that's different from a constant c that we had up here, and this is saying that f of t is actually a function. So this idea that f of t is a function, just saying that we have a function that is being multiplied, we have a scalar function that's being multiplied by a vector. So this is going to result in something that's similar to a product rule, except of course, one of them is a function, and one of them is a scalar function, the other one is a vector function. So the derivative of scalar function f of t times vector function u of t is going to be the derivative of f times u plus f times the derivative of u. So that's again exactly the product rule, except we're multiplying a scalar times a vector. If you remember our work with the unit tangent vector, we generally have a 1 over the magnitude of that vector playing this role of a scalar function on the outside of a vector function. So if we ever have to take the derivative of a unit tangent vector, this might come in handy for us. The dot product and the cross product each have their own product rules, and you can see that it seems pretty natural to think about this. So the derivative of r dot u is going to be the derivative of r dot u plus r dotted with the derivative of u, and you can say the same thing with the cross product. The cross of r of u, the derivative of the cross product is going to be r prime cross u plus r cross u prime. Okay. And then the chain rule, if you have a vector valued function and each of the t values or the t parameter is replaced with a scalar function, then you can use a chain rule. So it's a derivative of r of f of t and then times f prime of t. And you know that this multiplication times here is a scalar multiplication, because f prime is a scalar being multiplied with the vector r prime. And then this last property doesn't quite have a name, but it turns out that if you take the dot product of r with itself, and that happens to be a constant, then it turns out that r dotted with r prime is going to be 0. And remember, the dot product is 0 when the two vectors that you're dotting are perpendicular. And so in this case, this is saying that r and r prime are perpendicular to each other. Okay. All right, let's do a couple of examples. Here's one where we have r and u, and they want us to find the derivative of the cross product. All right. I'm not too interested in doing the cross product, so let's just go ahead and use the formula. And we will need a couple of derivatives here. We'll need r prime and I'm going to switch notations and use the angle bracket notation, and derivative of that's going to be 6 and then 12t plus 2 and 5. Oops, that's a negative 5. Put a comma between, and then u prime is going to be 2t, 2, and then 3t squared minus 3. Alright, so those are derivatives, and let's just say the derivative now, d dt of u, the vector u of t, cross r of t is going to be, according to this formula, it's the derivative of the first. Now my u and r are switched, so u is going to be the first function. So it's the derivative of the first. So that's 6 comma 12t plus 2 comma negative 5 cross the second function. The second function is r, so I look back at my r. That's 6t plus 8 comma 4t squared plus 2 minus 3 comma negative 5t plus the first, that's u, that's t squared minus 3 comma 2t plus 4 comma 3t squared minus 3t crossed with the derivative of the second. So the derivative of r is going to be 6 comma 12t plus 2 comma negative 5. Okay, now here in this expression we have to do two cross products, so why not do one cross product and take the derivative? Well, the answer is that this might be easier if you actually have the functions u and r given to you. But if you don't have it given to you, let's say you only have u given to you and you don't know what r is, then you may have to do this cross product where you just use one as an arbitrary function that you don't know yet before you do a cross product. So there could be some reasons to do this, although the result might seem more difficult than the original problem. That's because sometimes they use these things for proving other theorems. Alright, let's do a few more examples. Here are a handful of examples that are a little bit more abstract or theoretical, or some parts that we don't know if we don't know some of these things. Okay, let's take a look at that first one. The first one, we have the derivative of this, and then inside is r is a t squared instead of a regular t, so this is going to use a chain rule. And we saw a chain rule up here. That would be this rule over here. So we don't know what r is in this case, so we'll just say that the derivative of r is just r prime, and then we'll put t squared here. And then now we're going to do a scalar multiplication with the derivative of t squared, so that's just 2t. So whatever your r is, you'll take the derivative of that, and then you're going to put in t squared in there, and then you're going to multiply this by 2t. So that's your first result. The second one is this is not a dot product. This is a scalar function, and this is a vector function. And so we got scalar times a vector, and that's going to be the scalar product rule. So let's do that. The derivative of the first is going to be a scalar function 2t times the second. We don't know what s of t is, so I'll just say keep that as an s of t. And then plus the first, that's t squared times the derivative of s of t. And this is a vector. Okay, that's our second one. And then our third one is going to be a dot product rule. But the first function in this dot product is slightly more complicated. It's going to use this chain rule part. So when we do the dot product rule, we want the derivative of that, and so the derivative of that is r prime of t squared, but this is a function that's more complicated than a t, so we multiply it by 2t, the derivative of the inside. So that is taken as a vector. It's a scalar product, scalar multiplication, but the result is going to end up being a vector, and you're going to dot that vector with just the s of t. That's the second function, plus, and then now you have r of t squared, that's the original function untouched, dotted with now the derivative of the second function s prime of t. Okay. All right, so those are some problems that use these properties, and yeah, that's it. Good luck.